This is Lecture 6, Measures of Central Tendency. I want to remind you once again where we are. We are considering descriptive statistics. So we have a population and we have a variable. And for today's lecture, the variable will always be numerical. And we will be going back and forth between considering parameters, which would be descriptions or summaries of the variable in the population, and statistics, which is descriptions or summaries of the variable in the sample. By central tendency, measure of central tendency, I mean something that tells you the middle or typical value. So that is the intuitive sense behind the average. Average gets used a little bit differently in statistics than in everyday life. In everyday life, when we say average, we mean you add up all the numbers and divide by how many there are. In statistics, that is called the mean, and it's just one of several averages. So in statistics, an average is any measure of central tendency, anything that's attempting to capture the middle or typical value. We'll learn 2.5 averages. The first one is the mean or average, and that's the main one we'll focus on. I have a sample data set here. The numbers 1, 2, 3, 3, 4, 6, and 9. So I'm going to look at each of these averages on that particular case, and then we'll go into more detail. So the mean, the average that you're used to, is you add up all the numbers and divide by how many there are. In this case, there are 7, so you add up 1 plus 2 plus 3 plus 3 plus 4 plus 6 plus 9, and you get 28. 28 divided by 7 is 4, so we say that the mean of this data set is 4. And that's a reasonable sense of the middle of the data, but it's not the only one. The second one we'll consider is called the median. The median strip in a road is the line in the road such that half the road is to the left and half is to the right. The median of a data set is the data value such that half of the data is below and half is above on a number line. We would say half is to the left and half is to the right. So in this case, the number 3 has that property. There are 3 numbers which are less than or equal to it and 3 numbers which are greater than or equal to it. And notice, of course, that in this case, the median and the mean aren't quite the same. It might have seemed to you at first blush that the average always has half the numbers less and half the numbers more, but you can see in this case that's not quite true. The third measure of middle we will pretty much see once and never see again. That's the mode. The mode is the most frequent value, the data value that occurs more often than any other. In this case, the mode is also 3 because it occurs twice. All the other numbers occur once. The reason the mode isn't very useful is, remember, what we're mostly interested in is using a sample to infer things about the population. And I think it's probably pretty easy to see intuitively that if you pick out a sample of numbers, you're likely to get duplicates or not get duplicates somewhat independently of what happens in the general population. So the mode of the sample will often have nothing to do with the mode of the population. So for several reasons, including that one, the mode is not very useful, and we will barely mention it again. Let's talk more about the mean. First, I want to tell you how to compute it. Well, of course, you already know how to compute it. I'm going to describe it in a little bit more formal and technical language, even though you already know how to do it, just to get you used to this language, which we will use a number of times. So the first piece of the language is n. N is the variable we use to represent the number of data points. In our last example, there were 7 data points, so n was 7 there. We want a name for each of those data points, so there's n of them. We'll call them x of 1, x of 2, x of 3, up to x of n. So you have a variable with a different subscript for each data point. And whenever we want to talk about the elements of a data set, we will write it like that. And if you look on the right-hand side, you will, I hope, recognize the formula you're used to for the mean written in this language. That is, you add up all the numbers, x sub 1 plus x sub 2 plus dot dot dot, however many there are, up to x sub n divided by n. In the middle, between the two equal signs, you see a rather complicated formula, which is a more compact way of writing what's on the right. It's called sigma notation. That big thing that looks kind of like a capital E on the top of the fraction is the Greek letter capital sigma, the ancestor of our S, which stands for sum in this case. And you'll notice that the sigma has a little subscript down and to the right. It has I equals 1 written next to it. Up and to the right it has n, and then entirely to the right it has x sub I. Here's how you interpret that. It's describing a sum, in fact the sum that you see on the right hand side of the equation, and the way you unpack it is you let the variable I take on a series of values from the first, so I equals 1 tells you start at 1, to the last, the n in the superscript tells you end at n. So you let I run through all the numbers from 1 to n, and for each value of I, you plug that value of I into the formula after the sigma. So I equals 1, you plug in 1 into x sub I to get x sub 1. I equals 2, you plug in 2 to get x sub 2, all the way until you get to x sub n, and then the sigma says you add up all of those individual things. And of course we're still dividing by n. Okay, so the sigma notation, which you, I hope, have seen somewhere before, but I'm guessing are not too comfortable with, is something we will see a number of times. We won't have to work with it deeply, but you'll have to be comfortable with recognizing that the thing in the middle is a shorthand for the thing on the right. And finally, on the left, you see the Greek letter mu. It's pronounced mu. It is the Greek ancestor of our M, although it looks more like a U. If you write a capital M really fast, it kind of will look like a mu. And that is the symbol that's traditionally used for the mean, but here I have to add a little caveat. And the caveat is, as we've said before, the distinction between the population context and the sample context is so important and so subtle that we use all sorts of verbal cues and notation to keep them separate. You've already seen that the exact same notion can be referred to as a parameter when you're in the population context and as a statistic when you're in the sample context, just to remind you which context you're in. The same thing happens here. The convention, which sadly is not followed universally, is that when you use a variable to represent a parameter, you use a Greek letter. And when you use a variable to represent a statistic, you use a Roman letter. Roman letters are the everyday letters that we use nowadays. So that convention is followed rigorously for the mean. The population mean is called mu, Greek letter mu, and the sample mean is referred to by an x with a bar over it, and is pronounced x bar. If it helps, this convention kind of fits with our sense of the difference between the Greeks and the Romans. Because remember, the population is what we're actually interested in, what we want to understand, but it's something we never have or rarely have direct access to. So the population is kind of idealized. It's a perfect thing that we imagine, and what we see in the real world is only a reflection of that idealized quantity, which is very much the perspective Plato had. The real world was a reflection of the idealized world we should be interested in, and that pervades Greek thought, which tends, at least in our perspective on it, tends to be abstract, theoretical, and kind of intellectualized, whereas our picture of Romans is that they took those Greek ideas and turned them into concrete, pragmatic realities, which is very much in line with how we think of samples, if that's helpful. And again, I have to apologize. Well, that's the convention. It's not universally followed, as we'll see soon. Okay, so to get a sense of what the mean is telling you, I need to tell you what it looks like when you're looking at a histogram. So remember, the mean is a typical value. So it has value. You should think of it as a kind representative of a value in the data set. In particular, it has the same units as the data set. If you're looking at people's heights, then the mean will be measured in inches or centimeters or whatever the units that you measured people's heights in was. So that means on the histogram it should correspond to a point on the x-axis where the values of the variables lay. What point is it? It's a very nice description. It's the point where the histogram would balance. If you made the histogram out of blocks or something so that it had weight resting on the number line, the histogram would balance on the point, which is the mean. I will show you that in a moment. It gives it a nice geometric and physical feel, which makes the mathematics, it turns out, very nice. Its most important property is that it's affected by all the data points. If you change one data point, the mean will always change. And in particular, it's heavily affected by extreme values. It's pulled towards extremes. We'll say it's sensitive to outliers. So to explain the first point, I have this picture, and I have to apologize. These are pictures taken off the web, and they're not the clearest, but if I were drawing them, they'd be even less clear. What I have is a histogram of a very simple data set. On top, you'll see that there's the number 1, the number 2 twice, and the number 3. So it's a data set with n equals 4, and it has that simple unimodal symmetric histogram. Down below, you see the same thing made out of blocks. Now imagine a seesaw where each data point is a block placed at that point, and sure enough, the balance point, pretty obviously, is right at 2, which is, you can check, the average of the numbers 1, 2, 2, and 3. That's all clear. But now I want you to imagine moving that point 3 to a bigger point. Replace 3 with 5. Now we have a unimodal skewed right distribution, just to remind you of our terminology. And now, if you average those numbers, you get 2.5. Once again, if you look down at the bottom half of the screen, that is indeed the balance point. You see that moving that one value larger moved the mean up with it. It pulled the mean towards it. And if you move even further out, 1, 2 2s, and a 7, the mean is now 3. And once again, that makes sense as the balance point. You know that on a seesaw, points far from the balance point, small things far from the balance point can balance out big things nearby. If you've ever sat on a seesaw with your big brother or sister, or your little brother or sister. And notice in particular that the mean in the third example really isn't a very typical value, right? 3 is not where most of the data is. It's not where any of the data is. So the effect of that extreme outlier, we call it, is that it pulled the mean towards it arguably unreasonably slow. So in the presence of the outlier, that mean doesn't give you a very good picture of the data. So we need to talk for a moment about what an outlier is. An outlier is a data point which is far enough from the others to require an explanation. That is obviously not a technical definition. What requires an explanation? It's more of a explanation of feeling, or a definition based on feeling. And in fact, what qualifies as an outlier depends on the context and your attitudes towards it. Typically, an outlier is an error. For example, when I copy down everybody's GPA from the survey on the first day, if somebody had a 4.0 GPA and I left off the data point, I would give them credit for a 40 GPA. That would obviously be an outlier, far from the other data points. It would be just because of an error. Errors are the nicest kind of outlier in some sense, because often you can recognize them, and often it's clear what to do. In the case of 40, you probably can guess what the mistake was and fix it. But if you can't, since it's obvious 40 isn't true, you would just delete it. And that's a reasonable thing to do for errors, but outliers can also just be unusual events. And when they're unusual events, it is a really bad idea to delete them. I say this because in many statistics books and classes, and in some cases in the practice of statistics, people routinely throw out outliers if they meet some precise definition of outlier that they pick. This is an extremely bad idea. It's a bad idea because it's letting your notion of what the data should be tell you what the data is. Anything you calculate from your data after doing that is now not a reflection of the actual data, but of what your picture of what the data should have been is. And that is a dangerous habit to get into. On the contrary, I would argue that outliers typically are the most interesting data points. They're the last things you should throw out because an outlier has a story attached. When you see an outlier, what you should do first is look for the explanation. I'll give you one quick, my favorite example of this, which is a statistics book I used to use, had a large set of data of fish caught from some lake, I think in Sweden. In each fish, it had its length, its width, and its weight. And you could do nice examples of looking at the relationship between length and width, or length and weight, and as you can imagine, the longer the fish was, the wider it was, the heavier it was. And there was one fish that was an outlier. Now, we haven't talked about the relationship between two variables, so I can't go into a lot of detail here, but there was one fish that was way fatter and heavier than it should have been based on its length. Well, you could throw that out, or you could ask why, and the reason was it had just eaten another fish before it was caught. So it had big distended belly and was heavy, but wasn't any longer. So that's an outlier with a story attached. Here's another outlier with a story attached, maybe one you can more relate to. In 1984, the University of Virginia, well, to this day, the University of Virginia publishes on its website stats about starting salaries of their graduates by major. And you can see why that would be interesting. If you're choosing a major and you're concerned that you have a good starting salary, you can look and see what would be typical. If you're considering University of Virginia, maybe you'd want to compare how their graduates do in your field of interest compared to other places you're looking at. So in any case, the major rhetoric and communications in 1984, all the graduates in that program had an average starting salary of $55,000. I imagine that sounds like a lot to you. In 1984, it was quite a lot. And as perhaps you can guess from the name, or perhaps not, rhetoric and communication was not a highly desirable major. It did not reflect some sort of set of very precise skills like computer science or mechanical engineering or something where students can often command higher starting salaries. It was a little bit of a, frankly, default major. So that was an astonishing salary for somebody graduating rhetoric and communication. What happened? Well, here's what happened. There were about 100 graduates that year, and most of them made salaries of around $25,000. That seems more in line with what you'd expect. But one of them was named Ralph Sampson, who you may remember, if you're into this sort of thing, was the first draft pick in the NBA and made something like $3 million. If you average $3 million with 100 $25,000 figures, you get $55,000. So that average, in this case, told you nothing whatever about the typical experience of rhetoric and communication majors. It was dramatically influenced by one extreme outlier. So this illustrates both that outliers tend to have a story and that the story is worth figuring out, and that the mean is so sensitive to outliers that in extreme situations with highly skewed data, it's not the best choice for giving you the typical or middle value. In this case, the median would have done a better job. Why? Because the middle value here half the data is less than or equal to and half is greater than or equal to is $25,000, or roughly that, which is the typical value. And nowadays, if you go to the University of Virginia website, they report the median income. And in fact, it's generally true that when people are reporting income, prices, things like that, which tend to have highly skewed data, they would generally report the median. And if they don't, they probably don't know much about what they're doing. So that brings us to the median. Here's how you compute the median. You order the numbers from smallest to largest. If there's an odd number, like in our first example there were 7, you just pick the middle value. If there's an even number, there's no middle value. There's 2 middle values and you average them. Okay? We're not going to do this by hand in anything more complicated than the first example we did, so I'm not going to go into great detail. But I will say that to do this by hand for a large data set is actually really hard. It might seem to you, based on that first example and thinking about it, that the median is easier to compute than the mean, right? You could pretty much glance at that data, which happened already to be ordered, and say, oh, the median's 3, the middle value is 3, whereas the mean, you actually had to do a calculation that you might have even needed your calculator for. But in fact, that's an artifact of a small data set. In a large data set, it is way more work to sort the numbers and find the middle than it is to average them. That isn't so significant in the age of computers, but in fact, in large data sets, that is a bit of an obstacle to computing the mean, and more importantly, it makes in computing the median, and more importantly, it makes the median very difficult to work with computationally. I told you that the convention that I just taught you wasn't always followed, and my next example proves the point. There is no standard terminology for either the population median or the sample median. The most common terminology is to use an uppercase M for the population median and a lowercase m for the sample median, which of course does not follow the Greek-Roman convention I taught you. Sorry. What does it look like visually? Well, on a histogram, again, it has the same units as the variable. If you're talking about heights, the median height will be inches. If you're talking about dollars, the median income will be measured in dollars. So it's a point on the x-axis on the histogram. What point? The point where if you draw a vertical line there, half the area of the histogram will be to the left and half will be to the right. Not quite the same as the balance point. And what's its property? It is not sensitive to outliers. In fact, many changes in the data set won't have any effect on the median. Frequently, you can change one value and nothing happens to the median. Let me show you, in a couple of examples on a histogram, how mean and median look different. Here's some right-skewed data. Not sure how easy it is to see, but there is a green line representing the median and a blue line representing the mean. The median is pretty central to the main clump of data. The blue line, as advertised, is pulled towards the extreme values. It's pulled towards that long right tail. So in right-skewed data, the mean is above the median. Opposite happens in left-skewed data. In this picture, which is left-skewed, the mean in pink is smaller than the median in blue. And again, the median is pretty much in the center of the clump. The mean is a little bit more towards the tail. Symmetric data, the mean and the median are both in the middle, which is pretty close to the mode as well. They're both equally good. So here's the quick summary. In highly skewed data, the mean and median can be quite different, and the median is generally a better picture of the middle of the data. So if you're just trying to describe what's the typical data point, the median is probably a better tool. If the data is reasonably symmetric, they work out about the same, and the fact that the mean is vastly easier to work with is, in particular, it will be much easier for inference, means that most often, if the data is not highly skewed, people work with the mean. In particular, most of the semester when we're doing inferential statistics, we will focus on the mean. There are procedures for dealing with the median, but they're difficult. They usually introduce as much or more error than the feature. The middle as well introduces. All right, so here's what you should know walking out of Lecture 6. You should be able to define mean, median, and mode. You should be able to compute the mean and the median for small data sets. That's all I will ask you to do by hand. You should be able, looking at a histogram, to estimate the mean and the median of a histogram and relate them to the shape of the histogram. You should know, before you compute them, that in right-skewed data, the mean will probably be bigger than the median, left-skewed the opposite, and in symmetric data they should be quite close. Once we have worked with this, you should be able to understand outliers and recognize the effect of outliers on the mean and median, and be able to identify an outlier in a given situation, think about what the explanation for that outlier might be. You should be able to keep straight the population in the sample context and know that you use mu in the population context and x bar in the sample context. That's in principle a very simple thing, but in practice it will take a little bit of time to get used to that. And finally, in class, we will learn how to calculate the mean and median of large data sets in Excel, and we will practice that skill in various ways for the rest of the semester.